Now, today we are going to deal with the numericals in the elastic properties of materials. Now, till now, previous sessions we have seen all the derivations, expressions, the meanings of elastic properties, various plastic properties, and how a body can be made into elastic properties. All these things we have seen. Now, we go with the numericals. Now, start with the first numerical. Calculate the extension produced in a wire of length 2 meters and radius 0.013 into 10 to the power of minus 2 meters due to force of 14.7 newtons applied along its length. Given Young's modulus of a material of a wire Y is 2.1 into 10 to the power of 11 Newton per meter square. Now what is here? Calculate the extension produced. That means we have to calculate the change in the length of a wire of original length is 2 meters and the radius is 0.013 into 10 to the power of minus 2 meters due to force of 14.7 Newton. And Y has been given, that is Young's modulus is given. So what are the given values? Length capital L is 2 meters. R is given as 0.013 into 10 to the power of minus 2 meters and F is 14.7 Newton and Y is 2.1 into 10 to the power of 11 Newton per meter square. Now what is that? We have to calculate is the extension produced, that is small x. Now we know that Young's modulus is longitudinal stress by linear strain, that is nothing but Fl by Ax. That is F by A is the stress and change in length x by L is strain. So stress by strain, rearranging the terms, we get the formula Y is equal to Fl by Ax. Here F is the force, L is the length and A is the area of cross section and X is the extension produced. So here area is not given, but we know that area of a cross section of a wire is pi r square. R is given. So you can calculate A using the formula pi r square. So X is equal to Fl by pi r square. Rearranging the terms in the equation, Y is equal to Fl by Ax. Rearranging, X is equal to Fl by pi r square Y. Given values are F is 14.7 and length is 2. 14.7 into 2 divided by pi into r square, that is 0.013 into 10 to the power of minus 2 whole square into Y is 2.1 into 10 to the power of 11. Calculate using a calculator and you will be getting the value of X, that is extension produced is 2.6 into 10 to the power of minus 3 meters. So whatever we are supposed to find out, we got the value as extension produced is 2.6 into 10 to the power of minus 3 meters. This is the first numerical. Next we go with another one. Calculate the force required to produce an extension of 1 mm in steel wire of length 2 meters and diameter is 1 mm. Y of steel is equal to 2 into 10 to the power of 11 Newton per meter square. Now here in this numerical it has been given, what has been given? You have to calculate the force and the given length is 2 meters and the diameter has been given, Young's modulus has been given. So extension is produced of 1 mm, that means X is elongation, change in length is 1 mm. Convert 1 mm into meter, that is X is equal to 10 to the power of minus 3 meters. And capital L, length of a steel wire is 2 meters and diameter is 1 mm. So convert into meters, it is 10 to the power of minus 3 meters and Y is 2 into 10 to the power of 11 Newton per meter square. Now you have to calculate the force F. Since here diameter has been given, you have to calculate the radius. We know that radius is equal to diameter by 2. So you will be getting 10 to the power of minus 3 by 2, it is 0.5 into 10 to the power of minus 3 meters. And as seen in the previous problem, Y is equal to Fl by Ax, that is a formula for Young's modulus. Y is equal to Fl by Ax. A is the area of cross section, you can determine by value of R by r square and F is equal to Yax by L. Rearranging the terms for the above Y is equal to Fl by Ax, you will be getting F is equal to pi r square Yx by L. Substitute the value of R square, Y given, X given and L also given. Substitute the values and get the value. You will be getting F is equal to 78.54 newtons. So this is a force required to produce an extension of 1 mm in a steel wire of length 2 meters and diameter of 1 mm, having the Young's modulus of steel is 2 into 10 to the power of 11 Newton per meter square. Next, calculate the torque required to twist a wire of length 1.5 meters radius 0.0425 into 10 to the power of minus 2 meters through an angle of pi by 45 radians. If the value of rigidity modulus of the wire is 8.3 into 10 to the power of 10 Newton per meter square. Here what is been given? Length is 1.5 meters. Radius of the wire is given. R is equal to 0.0425 into 10 to the power of minus 2 meters. And rigidity modulus is also given 8.3 into 10 to the power of 10 Newton per meter square. And value of theta is pi by 45. Now what is that? You have to calculate the torque tau. Now we know that couple per unit twist C is equal to pi n r power 4 by 2l. So here n is nothing but rigidity modulus, r is a value given, l is also given. So pi into 8.3 into 0.0425 into 10 to the power of minus 2 whole to the power of 4, because r is r to the power of 4. We have derived this expression in the previous sessions. So using that formula, get the value of C as 2.8357 into 10 to the power of minus 3. This is nothing but a couple per unit twist. But here in the question it has been asked for the torque tau. So tau is equal to C theta, and tau is equal to, we have calculated the value of C into theta. Theta value is pi by 45. So 2.8357 into 10 to the power of minus 3 into pi by 45. Use a calculator, get the value of answer of torque tau is equal to 1.98 into 10 to the power of minus 4 Newton meter. This is the torque required. Next we move on to the another numerical. Next, fourth. Calculate the angular twist of wire of length 0.3 meters and radius is 0.2 into 10 to the power of minus 3 meters when a torque of 5 into 10 to the power of minus 4 Newton meter is applied. Rigidity modulus of the material is 8 into 10 to the power of 10 Newton per meter square. So what is been given here? Calculate the angular twist of a wire. That means theta you have to calculate. Length is given as 0.3. Radius r is 0.2 into 10 to the power of minus 3 meters. And torque tau is 5 into 10 to the power of minus 4 Newton meter. And rigidity modulus of a material is been given. Here it is similar to the previous problem, but only thing is here tau is given, you need to calculate theta. In the previous problem you have calculated tau when theta is been given using the couple. Similarly here tau is equal to C theta, where C is equal to pi eta r power 4 by 2l. Here n can be pronounced as eta or n, but that represents the rigidity modulus. So since tau is equal to C theta, substitute the value of C into this equation and rearranging the terms. You can rearrange the terms with the tau. Therefore, theta is equal to tau to L. Take from denominator to left hand side, cross multiplication, tau to L by pi eta r power 4. Tau is already given 5 into 10 to the power of 4. 2 L is already given 0.3 meters. And pi value is constant and eta is 8 into 10 to the power of 10 and r is 0.2 into 10 to the power of minus 3 whole to the power of 4. Calculate with the calculator, you will be getting theta is equal to 0.75 radians. This is the angular twist for the given numerical. Next, a rod of cross section of area 1 centimeter into 1 centimeter is rigidly planted into earth vertically. A string which can withstand a maximum tension of 2 kg is tied to the upper end of the rod and pulled horizontally. If the length of the rod from the ground is 2 meters, calculate the distance through which its upper end is displaced just before the string snaps. Young's modulus of steel is 2 into 10 to the power of 11 Newton per meter square and G is 9.8 meters per second. Now this problem is similar to the single cantilever, where one end of a rod of cross section area 1 centimeter into 1 centimeter, that is breadth and thickness are given 1 centimeter and 1 centimeter, rigidly planted into the earth vertically. That means one end of the rod is fixed in the earth and the other end and he is given a tension of 2 kg, is tied to the upper end of the rod and pulled horizontally. So this is similar to the single cantilever. Here mass M is 2 kg, thickness is 1 centimeter, that is 10 to the power of minus 2 meters. Even the breadth is 1 centimeter, that is 10 to the power of minus 2 meters. Length of the string, which can stand a maximum tension of 2 kg, is tied to the upper end of the rod and pulled horizontally. If the length of the rod from the ground is 2 meters, so length is given as 2 meters and y is given as 2 into 10 to the power of 11 Newton per meter square. Distance through which the upper end is displaced before the string snaps, that is the amount of depression we have to calculate, that is y0. You have to calculate it. So tension T is 2 kg. So W becomes mass into G, M into G. So 2 kg mass into 9.8 is a G given. So that becomes W. We know that Y is equal to 4WL cube by BD cube into Y0. This is the Young's modulus of a single cantilever expression which we have derived in the theory part. So use that formula to get the value. Here Y is given, W is given, L is given, B is given, D is given. So you have to calculate Y0. Rearrange the terms for the formula. Therefore Y0 is equal to 4mg L cube by BD cube into Y. 4m is 2, G is 9.8 into L cube is 2 cube and B is 10 to the power of minus 2 and D is 10 to the power of minus 2, BD cube, so whole to the power of 3 into pi is 2 into 10 to the power of 11. So substitute all these values, use the calculator, do the calculations and you will be getting the value of Y0 as 0.314 meters. Okay, this is these are some of the numericals. Thank you.